Good morning, good afternoon, good evening, and welcome to my post on recursion, renormalization, representation, and reality. Where does the air come from when water boils? The simplest answer is energy creates space and pressure contains space. You add heat energy to water, and this energy makes the water molecules speed up until there is no way for them to move any faster. At this point, they begin to collide, and when two particles collide, they squish out a bit of energy. When that energy has nowhere to go, it turns into space, a tiny bubble of space. Nature hates a vacuum, and all of the water is pressing in on that bubble, trying to make it disappear. So the bubble moves to cooler spots where the pressure is less intense. But lots of other bubbles have the same idea. So the bubbles collide and make bigger bubbles that rise to the surface. The surface tension of the water holds those bubbles in until they are big enough to break through and pop. The story is complicated by the fact that for very small bubbles, the internal pressure is very high, so high that they can't exist. So how can something that can't exist come into being? One popular explanation is that the surface of the pot provides a way for fractions of bubbles to come into being, thereby allowing them to be born and survive their trip to the surface. But this doesn't really mesh well with the story I just told in terms of particles colliding and squishing out energy that has nowhere to go. Which story is right, and how do you decide? I think the answer is found in the story of what happens when a bubble breaks through the surface of the water and releases its contents into the air. When something under pressure breaks through a surface barrier into a low-pressure space, it quickly cools. This is why your breath feels colder when you purse your lips as you blow out. But if you open your mouth wide and breathe out, you will create a cloud of condensation on a cold day. But the act of condensation releases heat, and that is why when steam hits your arm, it will burn you more than direct contact with boiling water would. Condensation is much like inverse bubble formation, and whereas condensation releases heat, bubble formation absorbs heat. The colder the air is, the more condensation will occur, and the hotter the water is, the more bubbles will occur. Condensation does not require a surface to occur, and that is why I think that explanations of boiling that rely on the surface of the pot are probably wrong. If they were correct, a pot of perfectly pure water would boil more slowly than a pot of water with dirt in it. If they were correct, you couldn't lower the boiling point by lowering the air pressure around the water as it is at higher altitudes, where it is easier for bubbles or energy to break through the surface of the water. If they were correct, you couldn't raise the boiling point by adding salt to the water. Salt dissolves into big, heavy, charged particles that attach themselves to the water molecules and slow them down. If the water molecules are like cars, the salt ions are like trailers attached to the cars that make it hard for the water molecules to move fast enough to collide with enough energy to make a bubble. If they were correct, water boiled in a mug in a microwave wouldn't get superheated. A mug has a large surface area for bubbles to form, yet they don't form even when the water has absorbed more energy than would be required to initiate boiling. When you superheat a cup of boiling water in a microwave, the water will look like it is not hot at all until you touch it with a spoon and it erupts in scalding bubbles. This suggests that the energy or motion required to form bubbles must be sufficiently random, as in a Tibetan bubbling bowl, where you ring it like a bell and bubbles form. If the motion in the water is too coherent, bubbles won't form, even if sufficient energy has been absorbed. In the Tibetan bubbling bowl, the vibrations make the water molecules move in and out from the center of the bowl. Eventually, the amplitude of their oscillations becomes so great that they collide with one another. When they collide, they make a bubble, and that jumps out of the pot. This might seem confusing at first, since we all learned about conservation of energy in our science classes, and we didn't learn about a conservation of space principle. But shouldn't there be one if energy is defined in terms of motion, which is defined in terms of space? Connecting these concepts to cosmology, one might wonder, if space literally expands, how can there be objects receding at speeds faster than light? And then decide that in Cartesian space, the bubbles observed in boiling water are merely an illusion caused by light losing energy to the vacuum. In Riemannian space, the bubbles are literally caused by space expanding. This is, however, a weird way to think. Nevertheless, thinking about boiling water is a nice way to understand why a pot of boiling water seems like it doesn't conserve energy, because some of the energy turns into space in the form of bubbles. In the same way, the sun does not conserve energy if you do not consider that the energy delivered to the system by the pressure of the vacuum or the pressure of gravity, which are two ways to say the same thing. When the sun burns, it must also create space, but that created space acts back into the pressure of the vacuum, keeping the sun bright. Are sunspots like bubbles on the surface of a pot of boiling water, or are they distorted gravitational shadows cast by planets? Are these the same things? Why doesn't everyone learn these stories about how water boils in school? My guess is that either science education is very unevenly distributed, or the teachers are afraid that we will figure out. I don't know what they're afraid of. In any case, people will eventually begin to understand how Einstein's modern physics of general relativity and quantum mechanics is an approximation of a more Cartesian recursive system. And when that is understood by everyone, there will probably be a crisis which buries this knowledge for a few centuries until researchers find it again. At least, this sort of renewal of foundations and removal of spandrels seems to happen periodically as the planet warms and cools. Today, most people have no awareness of these patterns and have been convinced by their betters that the sea is boiling hot and that pigs will soon have wings as a result of genetic engineering. What I know is that if you boil physics down to its essence, you are left with four things. Recursion is when you take the output of a function and use it as the input again and again. Renormalization is when you try to estimate the global properties of a substance based on its local properties and vice versa. Representation is when you create a description of a thing that exists in reality. Reality is the thing you represent through physics theories involving recursion and renormalization. This all sounds so straightforward. Where did physics go wrong? I think it got off track when it forgot how boiling water works and gave Albert Einstein a Nobel Prize for the photoelectric effect. If you shine a beam of light onto a pot of water and heat that water until boiling, would your theory of the average absorption and a reflection of the light's energy tell you exactly how many bubbles would rise to the surface of the water? No, it would tell you about the temperature of the water, a quantity only loosely related to the production of bubbles. In a metal, the absorption of light's energy is explained by Druda's skin effect, a surface resonance that describes how some waves are reflected and some are absorbed. When the distribution of metal is inhomogeneous, this can give rise to quantized localizations of energy, as modeled by Maxwell's equations and renormalization. But Druda's skin effect and Maxwell's equations and renormalization do not predict saturation effects, as in the pot of boiling water. Without saturation effects, field intensity can grow, and we know this can't happen. Quantum mechanics tells us that after a certain threshold, a quantized emission of energy will occur, like a bubble emerging from the bottom of a pot of boiling water. If you think of the metal as a film of boiling water heated by light, your water will never boil if you only turn the stove on and off all of the time, And on the microscale of a metallic surface, that is what a high-frequency wave is like. Similarly, if your stove heats up too slowly, you'll also never get it to boil. This is what I think of when I see the black-body radiation curve. Planck realized that if the energy is only absorbed in quantized amounts, that could explain why the shortest and longest wavelengths don't get absorbed. Einstein realized that this quantized absorption explained why increasing the intensity of light incident upon a metal plate doesn't cause more particles or bubbles to be ejected. But he interpreted this in a way that had been out of fashion since Newton wrote about corpuscles, quanta of light. Einstein concluded that light was both a wave and a particle called a photon. A minority of physicists still think that the idea of quantized light waves is a stupid idea, because if you can only ever measure particles with light, and light can only ever be measured with particles, light will act like a particle, or quanta, even if it isn't. Oh, my neck. Ouch. It can't be denied that treating light as a particle is convenient when making mathematical approximations of these systems. But the history of physics shows us time and time again that we make mistakes when we confuse approximations with reality. This is exactly what happened when the photoelectric effect demonstrated that Drude's model was merely a static approximation of a more dynamic quantized process that depended on a sort of saturation threshold, like a boiling point. There is a pattern to our efforts to look at smaller and smaller things. We approximate continuous processes with discrete processes, and then learn that we need to approximate these discrete processes with continuous processes, and so on. I think this suggests that real physics is recursive. From this perspective, it was stupid to give Einstein a Nobel Prize for interpreting the photoelectric effect as a rejection of the wave theory of light. This stupidity became amplified within the Rube Goldberg machinations of fundamental particle physics. 3 generations of fundamental particles are identified, but no reason is given for why there are 3 generations. Rather, the reason that there are 3 generations is considered to be mysterious. But whenever physicists see a mystery, they are usually being stupid about something fundamental. They tend to defend themselves from this charge by insisting that their job is to find mechanisms for things, but not reasons for things. For people who call themselves scientists, this is a very political maneuver. Their marketing game is even more on point when they insist that the simple explanations are too simple. The simple explanation of the transition from taus to muons to electrons, or from generation 3 to generation 2 to generation 1 particles, is that it is a state change as layers are melted away from a decelerating particle, as in a melting snowflake or a molecule breaking apart. In a Riemannian relativistic system, the faster something moves, the colder it acts, after all. But any well-trained particle physicist would shriek in horror at such an explanation, insisting instead on exclusionary, opaque language that says virtually nothing. In simple terms, each generation of particles has the same charge and spin, but a different lifetime within Riemannian space. A world where lengths contract and time dilates depending on your relative velocity. A world where people get terribly confused by clockwise and anti-clockwise motion. But what if changing one's perspective to that of a godlike Cartesian in absolute space shows that the lifetimes of the particles are all the same, but the charges are different because they are spinning by different amounts relative to an absolute coordinate system? This would certainly simplify things. What if Riemannian and Cartesian vantages provide different yet equivalent ways to describe the same system? A godlike Cartesian perspective would see that we have chosen to approximate things in Riemannian space as being in a steady state in which they all spin by the same amount and therefore all have the same charge. The Cartesian would see motion that we cannot see because we are trapped in a non-inertial reference frame, moving in sync with the things around us. The Cartesian would see that particles don't just pop into and out of existence, as the Standard Model says. They all exist in a permanent state, but their spin and charge change and make them appear and disappear from our perspective. After all, we can't see things that are out of phase with our particles, even if they must exist for our world to function in the way it does. In the most simplified language I can think of, things we see are in sync with us, and things we feel are out of sync with us. A Riemannian person indoctrinated in accordance with the Standard Model might insist that these ideas are inconsistent with conservation of charge, but I would say that when you change your perspective, charge will still be conserved. The charges and lifetimes of what you see will just look different. Likewise, Standard Model people tend to react badly to the idea that spin-up and spin-down electrons are the same thing as electrons and positrons. They say that shifting one's perspective from outside of an atom to inside of an atom seems to violate charge conservation, but that is so wrong. For a detailed explanation, see the notes at the end. Well, I guess I'll read those at the end. See the notes in the blog post. They help a lot. Charge is conserved within each perspective. A god can shift its perspective at will, and even if we can't do measurements with an absolute godlike perspective, we can certainly imagine doing so. Things get simpler when you realize that a transverse wave can be approximated by a spinning sphere, tumbling through space much like a generation 3 particle, an oversized bubble that tends to break apart into 2 smaller bubbles and some light. Those 2 smaller bubbles are spinning in opposite directions and thus glued together in a generation 2 particle as they continue to tumble through space. But they are unstable because the angles at which energy must circulate between them are too sharp. This is why 2 bubbles break up into 3 to form a generation 1 particle. Triangles are especially stable objects, and 30, 60, 90 triangles fit together quite nicely to make an isosceles triangle, a clock, or a Poincaré disk. If this story sounds similar to that of hydrogen, I imagine that it should if physics is as recursive or self-similar as it seems to be. Generation 1 is analogous to n equals 1, generation 2 is analogous to n equals 2, and generation 3 is analogous to n equals 3. You might recall that there is no stable n equals 4 shell within hydrogen, just as there is no generation 4 fundamental particles. These rules also probably apply on the scale of the solar system, and we just can't see the quantized patterns because they occur on average, and the time scales we can observe are too short to see them. On an earthly scale, we can get a lot of information about Schumann resonances, but still see the limits of our predictive power. One might have a perfectly accurate, deterministic set of equations for existence within a non-inertial oscillating reference frame. But if you can't know the initial conditions, all of your predictions of where the bubbles will appear in a pot of boiling water will have a certain degree of uncertainty in a quantum sense. And we all know that a watched pot never boils, as in ephemeral things like bubbles or fundamental particles can't exist if you keep disturbing or observing them. So, with that, I might read some of the notes, or I will not read the notes and I will direct you to the blog post to read more. And I am very well aware that the presentation style I've chosen to use here is very weird, but I'm kind of trying to play off of the creepy effect. Sometimes creepiness draws people in. I'm not really creepy in real life. It's just the character I'm playing right now.